welcome to that escalated quickly. My name is Sagi Dulce. I'm a senior security researcher for Aqua Security. Evidently, not with me here today is Michael Cherney. He couldn't make it, but no worries. It's for a good reason. He just recently had a new baby, so he'll be doing a lot of diapers, and I'll be doing this talk. So I want you to focus mainly on three things when we're going through a lot of slides and a lot of demos. We're going to discuss how developers are actually becoming new targets, especially if we're talking about microservice developers who are in charge of an entire thing, entire container, and how one infection can quickly spread through your entire pipeline. And the main course of this talk would be an advanced persistent threat against a developer running, in our case, Docker. We're going to dive into the attack. We're going to do 3 demos. It's going to make it feel like it's maybe a little bit overcomplicated, but just for the sake of education. It's not. It's actually a pretty feasible attack. And also, I want you to look out for 2 new types of attack that we're going to introduce today. And these are the host rebinding attack and the shadow container attack. And each one of those sort of stands on its own as a sort of a attack vector. So what's on the menu? Like you expected, containers and container development. Hopefully if you're in this room, how many people heard about containers, know something? Okay, so even if you haven't, we're still going to do a short introduction. Then we're going to dive straight into the attack. We're going to break it down to 3. We have a demo for each stage, so it will give you a sense of how it works. And finally, we'll just weave it on together with a full demo, and then hopefully have something smart to say about it. Containers. So what are they? If you have ever been to a talk about containers, you've probably seen this slide 100 times, so I don't know why you're taking a picture. Just yesterday I've been in a talk and I saw the exact same slide. So whenever you want to say what a container is, you always show a virtual machine on the left side against a container on the right. So if I'm a developer and I want to develop an application and I want to isolate it using a virtual machine, I see that I have a lot more work to do. I have to take care of the entire guest operating system. To spin up and take down a virtual machine takes a lot more time, and it's heavier than a container. And a container is simply a process that is isolated. It's running in its own little virtual world, so it has its own file system, network. It can spin its own processes, and basically it's a mini virtual machine that shares the same host, and you don't really have to add the entire guest operating system. And of course, I'll have the container engine that helps me manage these containers to start them, stop them, spin them up, or kill them. So that's good news. That's good news if I am a container developer, because now I can write, for example, Linux containers, and I can spin them up over Linux, obviously, and Windows also, and also Mac. So I can develop and run a container anywhere. And also, that it is a big game because also Microsoft are now actually enabling you to write and run Windows containers. And just to get a sense of how big this thing is, let's look at, of course, Docker engine. And these are some statistics from the beginning of the year, I believe, of DockerCon. They presented the growth of and the adoption of containers over the past 3 years. And we see pretty high numbers like 900,000, which is number of different Docker application on the public Docker Hub with over 12 billion pools and 14 million different hosts pulling together. So there's a pretty big community here of developers writing containers and users actually using and running containers. So if there's a big community, there's a big attack surface, and we have something to attack. So why not go after these developers? So developers are basically getting paid to write code and features. They don't get paid to do like things securely. So if security gets in the way, like you need to open a port on your Docker daemon to enable some tool to interact with it, but it's not that secure, maybe you're going to do it because it helps you like get things done. So these are people that are very technical, they have very high confidence, but almost by definition have access to sensitive data, like code, IP, and in the case of developing containers, registries. So if you take, like we said, a single developer, and now you move to like continuous development, so you're always pushing new microservices and containers out to production, even a single developer may cause your entire pipeline to be infected. So that's the intro out of the way, and let's jump into the attack, and let's have a bird's eye view of the entire attack. So all I ask for this attack to work is a victim running Docker, and the Docker daemon has a port listening for incoming HTTP requests. And that may look like I'm asking a lot, but like I said, the developer needs to get things done. And by default, for example, if you install Docker for Windows, in previous versions, that was the default installation. So whenever you install Docker for Windows, it has TCP port open, listening for incoming requests. And the second thing I'm going to do is simply get the attacker to visit some malicious website, social engineering, water holding, insert clever method here, whatever it takes just like to get him to visit the website. And then from there, we're going to escalate the attack. We're going to deep dive on a Windows 10 attack scenario. So like I said, we have 3 phases of the attack. The first phase, like many other attacks, it's a form of remote code execution, and we'll do that by simply abusing the Docker API. The second step is an attack we call privilege escalation, as it's a new form of attack similar to another attack that we'll introduce. We'll have an intro here and say why we chose to do a different form of attack. And that is a kind of privilege escalation over the Docker daemon. So now we'll have full control of the Docker daemon, and we'll ask ourselves what to do next, and the answer will be to run shadow containers. And shadow containers is a method of persisting inside the host, or more accurately, inside the hypervisor. So let's start off with step 1. So let's abuse the Docker API. So the idea to abuse the Docker API came to us when we tried to understand how does this magic work when you're sitting on your laptop running Windows, for example, or Mac. You run Docker run something, and you have a container running on your machine. Doesn't make sense. And there's, of course, no magic here. What happens is actually Docker installs a virtual machine on your host, and that's a Linux machine called Mobile Linux, and it's actually running Docker. And the container that you are running is actually running inside the virtual machine. And the Docker daemon on the host is actually talking through a virtual socket to the virtual machine. And finally, on the other side, you have the client, which can be command line or anything else, talking through a RESTful API with the Docker daemon. So this connection can happen over a Unix socket, it can happen over a named pipe, or like we said in our case, in the default installation of previous Windows version over TCP. So why not simply change the client to malicious web page and do whatever we want, right? So it's a little bit complicated. And the complication mainly comes from something called the same origin policy. And also, if you're not familiar with the same origin policy, when your browser loads up a page, it may look like the page is like this one single thing, but of course the reality is that it's made up of dozens of different elements. Each one can come from a different domain or host. So it's the browser's job to make sure that one element doesn't read or write data from another element that belongs to a different domain. And did anybody see underpants in the last slide? Okay, so you're paying attention. The rest of you failed. So it does so with something called the same origin policy. And the same origin policy simply says that if a request is not, the request is not from the same origin, if it has a different port, domain, or protocol. And if it's not from the same origin, if it's made across origins, then it's subject to more limitations. You can send any request that you want, only get, head, and post methods. You can't read back the response body of request, and you can't post a body, a request with a body to another element. So we said we don't want to start off the attack with doing something malicious. We want to start off clean. So we went ahead and list all the Docker APIs that didn't violate the same origin policy. And immediately, or after a couple of minutes, we said, okay, there's a single API call that looks interesting, and that is the build API. So when you are building, when it doesn't work. So when you're building a container, or an image more accurately, what you're telling the Docker engine is to look at a text file called the Docker file, and then go line by line, and you tell it how to layer up your image. And if you ever written a container, you've probably done this, or maybe done this 100 times, and maybe you didn't even notice, but there is a command here that is really enables you to do like bad things, and it is of course the run command. Because when you're building an image, you're actually executing code. So in my case, I can just load up whatever shell script that I want and run it. So if we dive deeper into the API call, we notice some interesting parameters. The first one is the tag parameter. So you can build an image and you can name it whatever you want. Makes it easier later in the attack to reference it, delete it, for example. The second tag is the remote tag. And that's also very interesting because it tells the Docker daemon to go ahead and pull your build context from a remote Git repository. So that's an entire command and control. So you can, depending on your victim, you can actually have the entire Git repository do some, I don't know, do ransomware, do reconnaissance, do whatever you want, and pull it and run it. And the last thing is the network mode. So now you can control what is the network stack of your running container. Is it running without a network? Not a good idea. Or is it running with a host network so that you can actually access the network stack of the host? So to demonstrate that this actually works so you can run code, we're going to do a simple reverse shell. And all we need is a simple post request. And that post request will be direct the Docker daemon to pull from our malicious repository. And in our repository, we simply have a reverse shell. So the demo and any other demo basically starts like this. So this is the victim's machine. He has the virtual machine running the containers. He has the Docker daemon on the host. And he has his browser visiting the malicious web page. So all the malicious web page does is issue a post command. It goes to the Docker daemon. It pulls from the GitHub, and now we have a running container. And that running container, what it does is opens up a reverse shell. So let's see how does it work. So this demo we show 2 windows of the victim and 2 windows of the attacker. And like many other demos, we start by listing images and the containers over the victim. So he has only one image. And all the attacker does is simply host the malicious web page using Python. And all the web page does, again, is it does a simple post message. And I'm waiting for incoming connections from for my reverse shell. Right, so now as the victim, I simply visit some malicious web page, and I'm seeing like the button that I can click, and then I get pawned, and I'll also see the entire building process feedback. But these are things that, like in a real world attack, you can hide from the user. And while the attack is going on, I can actually look at my Docker daemon and see that I have a running container and the images that that container pulled. And like we said, the container simply opened up a reverse shell back to the attacker. And here on the attacker side, I already have the shell, so now I can list the network interface, and I see the HV int 0 interface of the virtual machine. So we proved that we can run malicious code on the virtual machine by simply visiting a website without breaking anything, without doing anything too malicious. So when we notified Docker, they simply said, okay, so from now on, like many other installation, the TCP is simply an opt-in feature. So you can still configure it on any host, but it's not on by default. So let's move on to the second stage, and that is the host rebinding attack. So we ask ourselves, what should we do next? So we have a building container running, and we don't have full access to the Docker daemon API, again, because of the same origin policy. And the running container has actually a limited lifetime. It won't run forever. So we asked ourselves, what can we do? And I know what you're thinking. I can see it in your heads. Scream it out. Why not do DNS rebinding and bypass that pesky same origin policy? So again, if you spoiler, we're not going to use DNS rebinding. We'll do something else. Some believe it was discovered around 20 years ago, really became popular around 2007 with paper by Stanford, I think with cooperation with Dan Kaminsky. And then it spawned a lot of other talks in Black Hat and in RSA. What is DNS rebinding, how to protect against it. I think today there's also a talk in DEF CON talking about DNS rebinding. So just to get the gist of how it works, we're not going to deep dive into DNS rebinding. If I'm an attacker and I want to attack an internal IP address that I can't get through because of firewalls and stuff like that, I can set up a domain called attacker.com, and I get the victim to visit attacker.com. So he's going to query, he's going to perform a DNS query asking where is attacker.com, and I'm going to answer with 2 different IPs. My IP and, of course, the internal IP that I want to attack. Then it's going to do HTTP GET, load up some malicious script. That malicious script is going to pull, do another request, and now the attacker performs a TCP reset. And some versions of browser perhaps say to themselves, okay, there was a reset, I have 2 IPs, maybe I'll go to the second one. And now he thinks that the internal IP actually belongs to attacker.com. So now we basically bypass the same origin policy because there is no limitation. Everything that we can do on attacker.com, the malicious script can do on the internal IP. So like I said, we're not going to use DNS rebinding. First, because it may fail. It's an old attack. You can discover it. It happens like over your perimeter. You can detect it over the network. You can detect it in the DNS and block it. And me as an attacker, I don't want to set up a domain and maintain it and invest some money and make sure it doesn't get blocked. It's too much work. So instead, we're going to attack local name resolution protocols like LLMNR, which is a Microsoft protocol, stands for Local Link Multicast Name Resolution. Basically, it's DNS performed in environments where you don't have a DNS server. So every host can simply broadcast, says, hey, who knows such and such, and you can respond and say, this is me, or this is the IP address. So it's very easy to attack. Anybody can spoof responses and pretend to be somebody else. And what's also interesting that by default, your host will query every interface using LLMNR, including virtual interface. So of course, it will include the virtual machine. And if you spoof LLMNR replies, they don't get cached on the host, so it's the browser's job to cache them. And browsers do it for just about a minute. And we said maybe we can bypass that, and we successfully did so in Firefox. So in Firefox, if you simply delay the HTTP GET, the response for an HTTP request in half a second, it will get a little bit mad and will issue another LLMNR request. So instead of waiting 60 seconds to perform the attack, you can do it in half a second. So let's do the demo of host rebinding. Again, we're going to start with visiting we're going to start off where we already have a rebinder container running from the first step. And that rebinder container running's job is to perform the host rebinding attack. Now we're going to visit some local host called Pond on the same port that the Docker daemon is listening. So the first thing that's going to happen, it's going to query LLMNR, where is Pond? And the rebinder container will answer that he is Pond. So now we're going to load some malicious script, and that script's job is basically to wait out the caching of the browser. And it does so by simply querying for a path, and that path doesn't exist on the rebinder container. So it does so every 5 seconds, but finally the caching expires, and another request is issued, and this time the rebinder says, I'm on the local host. So now the same path gets actually an HTTP 200 from the Docker daemon because that's a valid request. So now we know that we bypassed the same origin policy and we can do whatever we want. Just for the demo, we're going to read some secrets from Docker, and secrets is like the most sensitive information. It's the password and keys and tokens that you want to protect. You put them in secrets, and we're going to post them back to the container. So let's see how that works. So I'm going to start off the demo with listing the secrets from my browser on the local host, and there's no problem there. I'm talking directly with the Docker daemon, and this is my secret. This is called my secret. And I'm going to run a rebinder container directly from command line, and it's going to use the host, the network of the host. So it does, like we said, it's spoofing LLMNR requests, and it hosts some malicious script. Now I'm going to visit Pond. I'm going to open the debug window and see the script in action. So this is the page from the rebinder container, and on the debug window I see that every few seconds I'm querying for the images JSON, and I'm failing. And this takes, like I said, about a minute, but for your convenience, we fast forwarded it. So it only takes, 20 seconds. So it will speed up a little bit, and after a minute, the caching expires, and we'll get an HTTP. We'll do the query again, and we get a good response, so we'll read the secrets, and then we'll post them back to the container. So from the container, we were able to read secrets from the Docker daemon. So to recap, The first step is abuse the Docker API and then get remote code executed. And this is a Rebinder container. So now it's the Rebinder container job to do privilege escalation and basically bypass the same origin policy. So now we have full access to the Docker daemon. So the question is, what do we do now? So we have full access to the Docker daemon. What do we do now? And the answer, there are many answers. We chose to go with something called shadow containers. So the problem I have is I can run a privileged container which will have full access to the virtual machine, access to the file system. I also have access to the internal network, but I'm not really concealed. Anybody can see my running container by simply doing docker ps. You'll see the container, you can kill it. And I'm not really persistent. And that is because whenever you restart your machine or whenever you restart your Docker daemon, the virtual machine is booting up from an image. So everything that you left on the machine gets deleted. And that is except, of course, for the state of Docker. So how do you make it persistent and concealed? So let's start by assuming to understand how it works. We already have a shutdown script written to the virtual machine. And the job of the shutdown script is whenever there is a shutdown, it runs a container. And I have another script which I call my script. This is basically the attack script. And this does something bad. This installs a kernel module or a service or scans the network or it does whatever, or ransomware. Whatever it does it inside the script, and this is the attack script. So once I'm going to reset the Docker daemon, it's going to run a shadow container. And the job of the shadow container is to save the script and the attack state inside the container, so whenever the Docker daemon boots up again, it's going to go back into the virtual machine. So now we have a sort of a ping-pong situation. So whenever you have the Docker container running, you have your entire attack inside the virtual machine, so the user and most other tools can't really see it. And when the when the daemon reboots, you have the state of the attack saved inside the shadow container, and when it boots up again, it goes back to the script. So we have a ping pong of between the attack on the virtual machine and on the container. So this is the actual code for a shutdown script that I use in this demo. It's a very simple code. First, I simply load into an environment variable my attack script, and I save it inside an environment variable on the container. I'm running a privileged containers, as you can see. I'm going to name it shadow, and I'm using a restart policy. So that tells the Docker daemon to continuously reboot the container until some condition happens. The image that I use is also not available, I think, in newer version of Docker. It's called the NSEnter, Docker for Windows NSEnter image. So in all the versions of Docker for Windows, when you installed it, it came with the NSEnter image. And even if you delete it and you reboot Docker, you still have that image. So it's the perfect one to use, nothing that contaminates the host. And the container is actually running the attack script. And here, for example, the attack script is also very simple, a simple if and else clause. So if the machine is actually booting up, I'm going to look if there is a persistent, this is the shutdown script. If it's there, then it means I still haven't booted up. If it's not there, I'm simply writing back the shutdown script. I write back the attack script from the environment variable. I install the shutdown script, and then I'm doing something evil. So my evil thoughts are not that sophisticated. I simply write a shadow file to the virtual machine. And then it commits suicide. So let's see a demo of running shadow container directly from command line. So if I go and run it from command line, it will look, before I run it from command line, I'll show you that I have nothing up my sleeves. I'll show you the images and the containers. So we have 2 images and 2 containers, and we'll use an inspector container, and we use that to look inside the virtual machine. So we see that we don't have any shadow files. So now we'll run this big command, which runs the shadow container. And after we run it, again, we'll list the images and containers. So again, I have 2 images and 2 containers, so nothing changed apparently. But when I run the inspector, I will see that I have a shadow file. There we go. So this doesn't prove anything, just that I have a file. I can also see the shutdown script that we've seen in the presentation. This is my script, the attack script, and we have the shutdown script. So to prove this actually persists, we have to reset the Docker daemon. And this is exactly what I'm doing. I'm going to reset it. This will take a couple of seconds. And once it's up, we're going to repeat the entire thing. Right. Yeah. So it's up again, and I'm going to repeat the entire thing. I'm going to list, I'm going to run the inspector. I'm going to use it a little bit later. And now I'm going to look at the images. So again, we have 2 images, 2 containers. Apparently nothing changed. When we use the inspector, we still see the shadow file. So we persisted throughout reboots. So now we have basically the final piece of the puzzle. So let's see the entire attack flow. So it's going to start off like all the previous demos. The victim is going to visit shadowcontainers.com, and the first step, like we said, we're going to abuse Docker API, and we'll get a Rebinder container running. The Rebinder container's job is to perform host rebinding attack. So now we have full access to the Docker daemon. So if I have full access to the Docker daemon, I can now run a privileged payload, and that privileged payload can write the shutdown script to the virtual machine. Now all I have to do is some housekeeping. I'll delete the Rebinder and the payload from the virtual machine. And now whenever we reset the Docker daemon on the host, it's going to create the shadow container, and of course when the daemon is up again, it's going to write down the shutdown script and my script back to the virtual machine. So let's see this whole thing working from end to end. So again, I'm going to show that I have nothing up our sleeves. We have 2 images and 2 containers running on the host. And we're going to use inspector again to look at the underlying virtual machine. And of course, there is no shadow file. Right, so let's start the attack. I'm going to visit shadowcontainer.com. And again, I'm going to click a button. We have 2 iframes here. The top one will show you the entire building process of the container. Again, in a real attack, you can hide this from the user. And on the bottom, we have another iframe waiting for the Rebinder container to load the malicious script and perform the host rebinding attack. So it will take a couple of seconds. I'm waiting for the Rebinder, and the Rebinder is now running, serving the malicious script and spoofing LLM response. So only while this attack is going on, you can actually go to the host and see the containers that is running. So I see the running container, the Rebinder container. I can see the images that it pulled, so I have some extra images from before. But this whole thing will be deleted after the attack is complete. And like we said, it takes a couple of time for the cache to clear up, but once it does, we get an HTTP 200 back to our malicious script, and now we can go ahead and run the privileged payload. So we run the privileged payload and we start it, and after we start, we can simply remove it and delete whatever images it pulled. So now, if I go back to the host, I'll see that I'm back to the first state. I have 2 images and I have 2 containers. So nothing is left behind. And again, we're going to use the inspector to look at the virtual machine. And we have the shadow file. But I'll nag and I'll prove that it still works by resetting the Docker daemon, so we'll know that it's actually persistent. And again, when it's back up, we're going to repeat the whole thing to prove persistency and that nothing is left behind. So the Docker daemon is up. Again, we're going to use Spectre, look inside the virtual machine, and we still have the shadow file. So the attack worked. And finally, these are again the attack script and the shutdown script. And finally, just to make sure there are no images left behind and no containers. So again, 2 images and 2 containers. So what does it mean? What we've actually saw is a form of APT, if we still use that word, advanced persistent threat. So we have persistency with the shadow container. We are concealed inside the virtual machine. We have a very low forensic footprint. And that is because the Docker engine on the host logs the initial step of the attack, but everything else that we do is inside the virtual machine. And you have full control of the virtual machine. You can manipulate these logs or delete them, and probably nobody's actually pulling logs from the virtual machine, actually looking at them. And we have persistent access to the internal enterprise network from that virtual host because he has access to the network. And possibly if the developer is running some writing microservices, you can infect the images that is writing, and you can infect the entire pipeline. So you may get the sense from the attack that it will only work on Docker running on Windows 10, but you can change the attack depending on your victim. So if it's running Mac, you can't do host rebinding attack because Mac don't use the Microsoft protocols. But you can still do DNS rebinding attack and then move back to shadow containers to persist on the Mac. You can do a similar attack on Linux, and you can perform again the DNS rebinding, and after you do so, you can run a privileged container which gives you full access to the host. So you don't really have to use shadow containers. You can choose to do so, but you can do something else. And the same thing is true for Windows containers. So when you're running on Windows containers, you can still go through the abusing of the API, host rebinding attack, and then when you run a privileged container, you have full access basically to the Windows host. So you can still run a shadow container, but you can do something else. So what should you do? Don't expose your container API. It's a bad idea. If you do have to expose it, make sure your clients are actually authenticated. And if you can't, for example, in some versions of Docker, it doesn't work to enable authentication, then simply block it. Don't forget to analyze your container engine logs. They may contain some interesting information, like if you're being attacked. Don't use NetBIOS or LLMNR if you don't have to. They're also very vulnerable to all sorts of attack. And the bottom line is you don't know how you're going to be attacked. So make sure you always scan images on the registries and always monitor your containers in runtime. So these are our Black Hat sound bites. They asked everybody who attended Black Hat to have a slide of sound bites. I think I'm the only one who did it. So developers are the new targets. There are two new forms of attack, like we said before, the host rebinding and the shadow containers. And please, people, protect your pipes, always scan images, and monitors the containers in runtime. We'll have a white paper on our website, probably also on the Black Hat website. And of course, you can hit us up on, or me, or whoever, on Twitter, or follow us, or follow up with questions. So thank you all for coming, and